Have you ever wondered how your phone unlocks just by looking at it? Or how your email inbox magically knows what's junk and what's important? Well, that's machine learning. And in this explainer, we're going to pull back the curtain and break down exactly how it all works, step by step. So here's our roadmap. We'll start with what machine learning even is, then look at the data that fuels it. After that, we'll dive into how the learning actually happens, figure out how we check its work, and finally zoom out to see the bigger picture. We're basically following the complete journey of how a model is born. Let's start with the fundamental question, right? How do machines get smarter? How can they possibly learn and adapt all on their own without some person having to write code for every single decision they'll ever have to make? And here it is. This is the big idea. Machine learning is all about algorithms that sift through data, learn from that data, and then use what they've learned to make smart decisions. It's not about following a rigid set of instructions. It's all about recognizing patterns. Okay, so you can't have learning without having something to learn from. And for any machine learning model, that essential ingredient, that raw material, is always going to be the same thing: data. So, in the world of data, we talk about two key things: features and labels. Think of it this way. If you're trying to predict the weather, the features are all the clues, the temperature, the humidity, the wind speed. The label is the answer to the mystery you're trying to solve. Is it going to be sunny or is it going to rain? And using those features and labels, models are usually asked to solve one of two types of problems. A regression problem predicts a number, something on a continuous scale, like how much will this house sell for? A classification problem, on the other hand, predicts a category, like is this email spam or not spam? All right, so we have our data, we've got our features, and we know our labels. We know what we want the machine to figure out. But how does the actual learning part happen? Well, it's not magic. It's definitely not some black box that you just flip a switch on. It's actually a very structured process, a clear workflow that takes us all the way from a huge pile of raw data to a working predictive model. This right here, this is the blueprint. First, you've got to gather your data. Then comes pre-processing, which is a super critical step because, trust me, real-world data is always messy. Only then can you pick the right model for the job and train it to find those patterns. After that, it's time for a reality check, evaluation. And finally, if it passes the test, you deploy it out into the real world. Every single model follows this fundamental journey. Now, that training step can happen in a few different ways. The most common is supervised learning, where the model literally gets an answer key. It sees both the questions and the right answers. But with unsupervised learning, there's no answer key at all. The model is more like a detective thrown into a room full of evidence and told, find the patterns. And you guessed it, semi-supervised learning is just a mix of the two. So we've trained a model, but this leads us to maybe the most important step of all: evaluation. We've to put our model to the test and ask a really simple but tough question. Is it actually any good? And this is a really, really important distinction. Did our model actually learn the underlying patterns in the data, or did it just memorize the specific examples we showed it? It's the difference between true understanding and just cramming for a test. When a model just memorizes everything, we call that overfitting. This is a model that knows all the practice questions perfectly. It gets 100% on the data it trained on. But the moment you give it new data, the final exam, it completely fails. Why? Because it memorized all the little details, the noise, instead of learning the general concepts, the signal. And the opposite problem, of course, is underfitting. This happens when the model is just too simple to even grasp the basic patterns in the data. It's like a student who didn't study at all. They fail the practice questions and the final exam. So the whole game is about finding that Goldilocks zone. You need a model that's not too complex and not too simple. Overfitting is what we call high variance. It's way too sensitive to every little fluctuation. Underfitting is high bias. It makes assumptions that are just too simple. The goal is always to find that perfect balance between the two. To measure how well a classification model is doing, we use something called a confusion matrix. Now, don't let the name intimidate you. It's just a simple grid that shows us exactly where the model got things right and where it went wrong. It separates the correct guesses, the true positives and negatives, from the incorrect ones, the false positives and negatives. And these two types of mistakes can have wildly different consequences in the real world. A type 1 error, a false positive, is like a spam filter sending a really important email to your junk folder. Annoying, right? But a type 2 error, a false negative, is like a medical test failing to spot a disease. See? Understanding which error is more costly is absolutely key. All right, so we followed the journey of a single model pretty closely. Now, let's zoom out a bit and take a look at the wider universe it belongs to and touch on a couple of bigger ideas. Okay, now we're getting to the heavy hitters. Neural networks are these incredibly powerful models inspired by the web of connections in our own brains. Instead of a single process, they use layers of interconnected digital neurons that all work together, which lets them tackle much more complex problems. So then, what's deep learning? Well, it's actually pretty simple. It's just what we call it when one of those neural networks has lots and lots of layers, making it deep. And that depth is what allows it to find incredibly subtle and complicated patterns, which is why it's the engine behind stuff like advanced image recognition and AI. But even with powerful tools like deep learning, it is so important to remember this one idea, the no free lunch theorem. It's a fundamental concept that basically says there is no silver bullet. No single algorithm is the best solution for every single problem, which is why that model selection step we talked about earlier is so important. And that's where we'll end our journey. We've seen how a model's built, how it's trained, and how it's tested. But understanding the how really just unlocks a much bigger question. Now that we have these tools that can learn from data, what new problems can we solve? What new questions can we start to ask? That is the real frontier.